Great. So just to start off with, I want to talk to you a bit, briefly about Draw Something. I just downloaded it on my iPhone here, and I'll show you a video actually so you can see. So Draw Something's a game for the iPhone. I think they've got an Android version out there. But essentially, as I understand, what you're supposed to do is you're supposed to you give a word or a noun, and you've got to draw it on your phone, and the other person has to try and guess what you're drawing, and they get letters start appearing to tell them what they're drawing. But we'll watch a video and you can see how it works. And it's made by a company called Omnipop.
Folks, it's John Q here from Techno Buffalo. How's it going? Welcome to another episode of What's the Apps here on Revision 3 and on Techno Buffalo. Today, let's draw something.
Very exciting.
Draw Something, a game created by gaming company OMG Pop, is somewhat of an overnight sensation in the mobile app world, with I believe over 30 million downloads across iOS and Android. Crazy! And there were even words of Zynga, that huge gaming company that basically owns everything, including Words with Friends, being interested in buying the thing. Nuts! Draw Something is basically Pictionary simplified and mobilized, geared towards users of all ages. You can log in via Facebook, which is handy, or you can make an account with their 1 to 2 step simplified process. To play, all you gotta do is find a friend via Facebook, username, email, or you can even challenge a random player, which could be quite fun. When it's your turn, you choose a word and start drawing. The stars indicate the difficulty of the word. If your friend guesses your word correctly, you and your friend both get an equal amount of stars, which can be used to buy additional add-on colors. Drawing something definitely has to be the best part of the game. Draw something. See what I did there? The drawing part is very, very bare bones. No mobile Photoshop here, but I believe it adds to the fun. You can adjust both brush sizes and colors. You also have an erase tool and trash tool, which clears your canvas. Guessing is also pretty neat. You're given a handful of letters that make up the word, so it kind of adds a funky Scrabble-ish element to the game. The game is incredibly fun and very, very addictive. Game concept-wise, solid 5 out of 5, Clap, clap, pat myself on the back, fist pump till the sun goes down. But execution-wise, there were a few flaws, at least in my opinion. When it's your turn to guess, you're forced to watch the previous round with the choice to skip. I feel that you should go right into the gameplay, with the option to watch the previous round if you wanted to. On top of that, you have to watch an animation that you can't skip, no matter what. While watching the drawing, there's no way to pause, rewind, fast forward, or replay. This, of course, might make it a little bit difficult and frustrating to guess what the other person is drawing, especially if they draw in sequences or if they just aren't very good at drawing. Apologies to the people who have faced. I'm a pretty good drawer, okay? I give you guys good drawings, and you guys just chicken scratch all over. It's fun though. Still fun. Still fun. And while you're in game, there's also no way to lead to the main menu. You either solve or you pass, which then breaks your streak. Drawing-wise, would be nice if you can zoom in, especially if you have smaller screens. Worst of all, the game doesn't seem to push notifications properly. For example, I might be waiting on the other person, but in actuality, it's my turn to draw or my turn to guess. And in order to continue with the game, I have to close the app and then reopen it to click that the green Get Ready button. Get ready to be destroyed by my awesome drawing or guessing skills. And speaking of whatever I was just talking about, I'm going to take some time to thank our wonderful friends at Domain.com. Domain.com is perfect for that moment when
I'll stop there. Anyway, so that's Drawing Something. So I've got it on my computer here, and I thought I could pass it around and you guys could have a try. Looks like I don't have too many friends who have it, but let's see here. So that's the interface, and you can try drawing one of those. That's going to be sent to my friend Nicola. So you pick one and see how you go. So I want you to have a look to see what you think of the interface and the game in general. And I guess the game has a couple of elements. So first of all, the social element. So you draw, you pick a friend, and then you draw something, and then you have to send to the friend. And what are you drawing there?
A bee.
A bee, okay. So that's the 1-star one, I guess. But the interesting thing with this, I think the game's been out now for 2 months, I suppose, or a little over a month. And as he said on the video, they attracted 30 million users so far. It's a free download for the game. But the more interesting thing is that yesterday Zynga bought the company, and they bought them for $200 million. And so quite a huge amount of money. The OMG Pop had been around for a little while as a game company, but hadn't really been that successful. They'd made a bunch of iPhone games, but they didn't really hit very big. But with Draw Something, it just took off like crazy, and they got lots and lots of users straight away. What's your bee look like? You've seen it already, huh? Okay.
So is it not real time?
Oh, well, they have to now, I think they get a message and then they got to guess.
Oh, yeah.
And then, yeah, so.
I've seen one where kids, I don't know what the object of the game is, but
they draw real time.
The lines are coming up in real time.
Oh, that's cool. So let's create another game. You guys each have a drawer. Do I have any other?
Does it have like a hot seat mode?
I don't know. Let's see.
Because that would be quite fun for like car trips for kids playing in the back seat.
Oh yeah, well, if you got two, yeah. So if you had a tablet, you could draw. So here you have a try drawing, or you can pick up new. And I guess when you guess, you get coins, and then you can spend the coins. You can spend the coins to get more colours, something like that. But it's interesting that Zynga paid so much money for it, and I think it was for a couple of reasons. One was because they had a big user community, so they had 30 million users and going up. And secondly, because they're kind of tapping into a new class of gaming apps. So these are kind of, I guess you could say they're social games, but they're very lightweight kind of social games. So you another example is Words with Friends, where I don't know if you played that one on your phone, where you play Scrabble and you play with your friend, or so any of those games that you can. So with this, you can obviously play in a matter of a minute. You know, you're in the toilet or in the bus or something. You can draw, and you send it off. And how'd you go?
It's like a sort of what sort of genre is that? It's like turn-based or something. Yeah,
well,
turn-based.
I guess you'd say it's a lightweight turn-based social game, probably. But interface-wise, it's very, very simple. But you can see it can be quite. Oh yeah, just pick one of my friends. Doesn't matter. They're all friends, so that's all good. Yeah. So, what's your impressions of playing?
It's quite hard to draw. I mean, they're fine.
Yeah.
On a tablet.
I'll see if any of my friends reply back during the lesson, and then you can see the other side where they draw back, and we get to guess what they're doing. As you said, they put words up on the letters up on the bottom, and so you guess with the letters you got there. Anyway, I just thought that was very interesting about how they've developed a pretty nice user interface, but then tapped into the social gaming market, and you know, in a matter of a couple of months, this one application increased the value of their company by tenfold or something, to the point where Zynga want to buy it.
So you got a current game or something?
The current game.
Oh, do you have to start a new game?
Yeah, just create a game and then just hit Facebook and log in with my Facebook account.
So it's quite an interesting market because, like, I don't see that I'd play that game for very long. It'd be real novel, and then I'd probably stop playing it.
Yeah, have you played Words with Friends though?
Oh, I've seen it.
Okay, so
Yeah.
it's a Scrabble.
But I guess, like, for me, that's sort of not really the games I'm interested in.
Yeah.
So,
Well, if you're interested in first-person shooters or something else, then it's not going to hold attention. But with these smartphones, some of those lightweight games are really good because you've got like a minute to play. You're in a doctor's meeting or you're waiting to go into a lecture or something. You've got a minute or two to play, and you can play something for a couple of minutes without having to like log into a strategy game and be playing for 10 hours or anything like that.
Yeah, exactly. Those things take like an hour long.
Yeah,
sometimes,
sure.
So.
And this one has probably a social component. I don't know if they're smart. They've probably got it so you can trash talk your friends or something. So
Oh, yeah.
yeah. Okay. So 4.
So one thing that I was sort of worried about that first came to mind is people drawing like lewd images.
Well, there's no reason.
I guess it's your friends though, so like.
Yeah. Well, you can play against strangers, but yeah, you could have
Then you get like that.
draw naked people game or something. Yeah. So yeah.
Well, because there was that chat roulette that sort of
Yeah,
that went a bit weird.
Yeah, that was a big hit. Well, there's something else. There's something about having a social component. So when I was we developed one of the first collaborative AR games, and we were trying to think about, we had the AR toolkit, and we could put AR objects on cards, and we were trying to think about a game that people could play that would keep them engaged. And we had all these complicated ideas like playing Battleship and Monopoly and all these different things. And in the end, what we came up with was a card matching game where you could just have to play. We had cards that had different images on them, and you had to match images that went together. So there was a horse and a cowboy, and you put them two together. So when you turned it over, you'd see the cowboy and you'd see the horse. And you put the two together, then you see an animation of the cowboy riding the horse. And there was a UFO and an alien and different things. So very, very simple, but people found that really engaging because the key was that it was a collaborative game. So you stood across the table from a stranger, you turned your card over, and you had the alien on it or something, and the stranger had the UFO, then immediately you wanted to put it together. And people were just fascinated by being able to hold objects up and look at them and being able to talk to each other. So we didn't have to put any complicated gameplay or anything in because there was a game. And people would play that for 20 minutes, even though it's really simple, just because of the social engagement. So it's the same with the chat roulette. The technology itself was very, very simple, but by having that social component in there, that drew people in. And then you had all these kind of really strange emerging behaviours happening. Like there was that guy that was the pianist who would make songs about people he saw in chat roulette. So whenever he would chat with people, it was strangers, and every minute or two somebody else would come up and he'd start singing, "Hey, pretty girl with the blonde hair," and everything. And so,
Funny.
Anyway, so what I wanted to talk today was a bit more about the graphics, and then we'll talk a little bit about Arduino. Then next week we'll talk about open frameworks. I'm also working with Michael to put together a assignment, and I'll get that to you next week, and then you can work on it over the holiday. And the basic idea of the assignment is to do a project that combines processing with some physical input, with the Arduino input, and then but it'll be a simple project, and it'll be due the end of the first week back. So you should have about 3 weeks actually 4 weeks to work on it. But I know also during the holiday break you've got your, there's a small 1 week project you're going to be doing, and you have to think about your thesis as well. The three of us, Christoph and Andreas and I, we'll get that next week too. It'll be fine. And there's also going to be a small change. I'll be teaching my class on Tuesday morning next week, not Wednesday. Because on Wednesday lunchtime I'm taking off on holiday for 3 weeks.
Are we going to do an assignment on open frameworks?
Probably. I'll have to talk to you about that, see how confident you feel. There were supposed to be 4 assignments, but I think we'll make it 3 instead. And then the idea was to have 1 assignment on the user interface design, which you've done, 1 just on processing, 1 on Arduino, and a 4th one which was on integrating everything together. Oh, yeah. But it seemed like you guys wanted to work more on software than hardware, so the Arduino wasn't as interesting.
Yeah,
so
we've got quite a lot of hardware already, like items that are sort of pre-made, and they've got like signals that we can tap into.
Yeah, sure. So I thought I'd combine the Arduino and the processing together, and then we'll have to think about the 3rd assignment. And it probably be a assignment you could do with either processing or with open frameworks. So because open frameworks might be more of a learning curve for some of you, depending on how it goes.
I've been playing with it now, sort of finding it pretty intuitive. So.
Oh, cool. That's great. Okay, so let's talk about graphics. So what we're going to talk about today is about transformations, a little bit about animation, and pixels and textures. So I talked last week about 2D graphics, and we talked about how you could move the canvas around a little bit, and we looked at this example of this arm, and so we're going to talk more today about 3D graphics, and we touched on it last week, but I'll go into more depth this time. So with processing, you've got 2 options. You've got the P3D library or the OpenGL library, and essentially the main difference is that OpenGL library provides, if you've got it uses the hardware acceleration on your computer, so it can be faster and have better rendering, but it's also more complex. You can also use the effectively native OpenGL calls, and I'll show you that a little bit later. The P3D library is really easy to use and simple, and it's integrated directly into processing as well. So I showed you this last week, which was a simple scene. The main difference with using the graphics is that when you set up the size function in processing, is you have to pass it a P3D argument. That tells processing that you want to do 3D rendering. And then you can create a scene like this. So in processing, you can define your own shapes. And so what you need to do is specify a list of vertices and then say whether or not you're going to use quads or strips or triangles. And then you have to have a begin shape and an end shape bracketing the shape you're using. So here's an example of a cube. Well, a square, sorry, is 4 points there. And also there's this fill command. The fill command is used to specify the color at each of those vertices. So you can specify the color and the vertex position as well. So I'll show you a couple of very simple demos. So this is a first of all RGB cube, and there's a vertex demo as well. So let's fire that up. Okay, so in this case, you can see this long list of vertices here. That's those 6 vertices are specifying the cube vertices, and then they're all set to different colors along there. And then what processing does is it works out the in-between values between the colors. So if I run that, then you've got the cube here, and I can rotate it around, and you can see it's a nice colored cube. There's some other interesting things with the code as well, though, I can show you. One is they've got the scale function here, so you can set a scale, and that scale applies to the whole cube. As I said before, the cube is bracketed by quads, so it's saying you're specifying, it's taking 4 vertices and using them to specify one face in a quad.
It's interesting that so it doesn't have an in shape between each face.
No, because you're building one shape, so that glues all the faces together. So basically, you specify a set of 6 flat polygons, and you glue them to one shape. Yeah. The other part is the mouse manipulation. So the way that works is it just takes the mouse position and it uses it to specify rotation around the X and Y axes. So that's these 2 lines over here. And there's also a translation function which moves the cube into the middle of the screen to start off with. So it's pretty straightforward. The one thing...
How's it doing the blend? Is it?
It automatically blends it. So when you take... so this corner here, for example, is blue, obviously. So that's RGB, so that will be 001 for the fill. And this one over here is green, so that's 010, and then it automatically just blends between. But I'll show you a bit later how you can apply your own textures as well. And the whole thing is encapsulated in a push and pop matrix, and we'll talk about that a bit more, but if I turn this off, I think it's going to go haywire. Let's have a look and see if it does that. Didn't have much luck with that last time, so we'll see. Oh no, it doesn't do anything. Okay, that's fine.
You just do one and not the other.
Yeah. So that's the RGB cube. The other one I wanted to show you was the demo vertex demo. Processing's having some trouble here. I need to quit some applications. Too much going on. Let's see here. Just not opening. Let's see what else I can quit.
Oh, sometimes you need to put out a processing and load it up
Yeah.
again.
Well, I think I've got a lot of stuff going on my gene as well, so the memory stuff. But let's try again.
Nice.
There we go. Okay. So this one's a bit more interesting because it has its own drawing function. So what we just drew before was a cube with specifying the polygon faces. In this case, they've created a function called draw. Well, this is the main draw code, so it's very small. Translation, and again that mouse rotation, and then this function called draw cylinder. What draw cylinder does is it draws a cylinder. So you can specify different arguments to it. So in this case, you specify the top radius, the bottom radius, how high you want it to be, and the number of sides you want it to have. So this first one is uncommented, so the top radius is 10, the bottom radius is 180, and it's 200 high, and it's got 16 sides. So if I commented that out, and then uncommented this one here, this has got the top and bottom radius the same, so it's going to draw a straight cylinder, so we can run that one. And it's got a lot more sides, it's got 64 sides rather than 16, so you see it's very, very smooth there. And or I can, this bottom one here has only got 4 sides, and it's got 0 for the top, so it's going to become a 4-sided pyramid. And you can see there it is there. But the drawing function is kind of interesting. So what you'd normally do in processing, if you're doing a complicated drawing, is you'd write a drawing function for what you're trying to draw. So in this case, they first of all drawing the top and the bottom. So they've created the quad strip, and they've then create all the vertices, and they do a begin shape and end shape. And then for the sides, they create a triangle fan. So quad strip, you have to provide 4 vertex values, and you draw the quad. For the triangle fan, it just connects alternate triangles together with alternate vertices together with a triangle. And so they have 2 different drawing methods, and they stick them together to make a shape. So those are both nice examples of how you can create shapes. So the next thing I want to talk about is transformations. So in processing, you can do rotations, translations, and scales, and you also have push and pop functions. So it's pretty straightforward. You pick a rotation to rotate about one axis. The translation, you can either translate about x and y or x, y, and z. And the scale, you provide a scale value. What processing is doing underneath the hood is creating matrices and translating the points depending upon matrices. So, for example, if this is a translate where you want to move an object in the x, y, and z direction, then you would create a matrix like this, and the last column would be in the x, y, and z direction. And then what happens is it takes your current position here, multiplies it by the matrix, and it will translate it to the new position. So this all happens inside processing in the internal, so you don't have to know about it, but you just have to be aware that underneath the hood, what's happening is that processing is generating these 4x4 matrices and concatenating together all your points. Similarly, you can use the same thing for scaling. When you're doing a scale, then what you do is you change the first matrix was an identity matrix around the diagonal, so it didn't change the points at all. But in this matrix, you apply a scale factor along here, and you can see how that would work because the new value of x you want to multiply by the old value of x by the scale factor. And you can apply different types of scaling. So if the scaling is greater than 1, then obviously the object's going to grow. If it's less between 1 and 0, it's going to shrink. But if it's a negative scaling, then you can flip the objects around and you can change and mirror them as well. So here's an example of a reflection about the y-axis. So basically you take every x point and you flip it around. So in that case, you'd have a -1 on this diagonal, and then when you multiply it through, it'll rotate it. X dash becomes -1 times the original x value. And the last transformation is rotations. So in processing, you just have to provide a simple rotation command. What's happening underneath the hood is that you are changing the diagonals or the off diagonals of the transformation vector. So when you rotate around the x-axis, which is around the z-axis, which is coming out of the board, then you are changing the x and y coordinates according to this equation here. And similarly, you can rotate around the x-axis and you'll change the y and z coordinates. And you can rotate around the y-axis and change the z and x coordinates. So you basically, in each case, you're generating a set of rotation matrices. Again, you don't have to remember this so much, but this is what's happening under the hood. And if you do a lot more graphics, you may come to the point sometime where you have to actually do the rotations by hand or something like that. One of the very important things, though, is the order of transformations. So you can see here, this is a rotation. There's a little house or something around the origin. You rotate it first and then you translate it. And this is the opposite. This is a translation first and then the same rotation. So you can see the end result is quite different. In this case, you've got the house tilted along the x-axis. In this case, you've got the house up in the air somewhere here. So it's very important to think about in processing and in other graphics programs what order you're going to do your transformations in. And this is because the final set of coordinates is a composite of all the transformations before that. So if you wanted to do a rotation, like if you had the first case here where you're rotating then translating, then what you do here is that Q1 would be the rotation and Q2 would be the translation. Or if you wanted to translate first and then rotate, then you swap it. The Q1 would be the translation and Q2 would be the rotation. So this is some OpenGL code, but the principles are pretty much the same in processing. So in OpenGL, it post-multiplies the current matrix. So in this case, this is the rotation followed by translation. But the order, it seems counterintuitive, but when you put the code together, it's translation first and then rotation. But the way to think about it is you start with your vertices, your vertex here, and you go back upwards. So the vertex is here, and then you're applying a rotation and a translation to it. So I wanted to give you a little demo. Oh, well, let me talk this through first of all. So in this case, if you wanted to do a translation followed by rotation and another translation, you'd have them all going in sequence, and then you would internally, processing multiplies all of these matrices together to generate a final composite matrix that is used to transform the points. So in this sequence here, you've got the, you're first of all doing this negative translation here, and you're rotating about the z-axis, and then you're doing a positive translation. Yeah. So one of the problems is that if you apply several sets of transformations to different objects, the transformations can accumulate. So if you've got an object that you rotate and then the next time through the rendering loop you rotate it again or translate it, then it starts accumulating. So that may not be what you want to have. So the solution to this is that in the graphics program they create a stack of transformations, and each time through you can reset to the identity matrix and apply a new transformation to the stack. So I'll show you that here. So this is OpenGL code, but the same thing as in processing. So here they have this load identity starts off with identity matrix, and you've got a rotation, a translation. So this is the current transformation here. Then what they do is they do a push matrix, and then they apply a scale transformation. Then they do a pop matrix, which means a scale transformation disappears off the matrix, and you're left with this one down here. So what you want to get is that each time through, you're always left with the current transformation. If you didn't have the push and pop, then each time through, you'd be adding more and more scale transformations on here, and the object would get smaller and smaller, or bigger and bigger and bigger. So it's really important in processing to put a push and a pop around your rendering code to make sure that you don't accumulate the transformations. So here's another example. If you were drawing a house, probably what you want to do is you'd have a scene and you'd translate or transform somewhere and draw the house. But then you'd probably have a function called draw house, and inside that function you'd have some commands to draw the components of the house. So that's what they've got here. They've got this sets up the identity matrix, then it translates somewhere for the origin, and now you're going to draw the house. So you push and pop, and then inside that you move the house 10 along the x coordinate, you scale it, and then you have this house draw command, and inside the house draw command you have a command to draw a door and a window, and again they're surrounded by push and pop commands. And then when you pop out of that, then you might want to draw some trees, and again you push and pop. So let me show you an example of that working. Let's see here. So if I go back to the push pop demo. So what I have here is very simple demo. There are 3 cubes here that are slightly offset from each other. You can set the number of cubes by setting this number here. So in this case I set 3. You can specify an offset. So actually we should change that. We'll make it pi over C over... No. You're living life on the edge there, aren't you? So you can blow it up. So we'll make it pi over 8. So it'll be a larger angle offset. So it'll be easy to see. So they're all offset by pi over 8, which I guess is 360 divided by 8. What's that? 35 degrees? No, 45 degrees. Yeah. So they're all offset by 45 degrees each. No, it's 90. Pi is 180 though, isn't it? So it's yeah, it's not so it's it'll be 20 something degrees. Probably not a good one to choose. Anyway, so that you can see they're all offset like that. But what's happening here is that there's it loops up the number of cubes, so it loops up to 3. It fills them, and each one is filled with a different color. It rotates them about the x and y axis by the offset, and then it draws a box. But if I take out the push and pop matrices, then you'll see something else happens. So if I take these out, then what will happen is the rotations will accumulate, and instead of the objects being at a fixed rotation with each other, every time through the rendering loop they'll rotate more and more and more. So you'll see that happening now. So now what you see is the cube in the middle. Well, all the cubes are rotating now. They're not at a fixed rotation relative to each other. I guess could be quite beautiful, but maybe not the effect you're after. There's another demo I can show you, which is a larger cube demo. So if I run this one called Push Pop Cubes, this one's going to draw lots and lots of cubes on the screen. So in this case, they create a cube class, and there's going to be 21 by 21 array of cubes. They've created a cube class. So here's the cube class. It's pretty simple. Each cube has a width and a height and a depth, and they can be shifted around. And then inside the cube class, there's a draw function. So you have the list of all the quads there, using the width, the height, and depth with the shift x, which specifies how fat the cubes are going to be. And so there's a simple thing here. Last week I think you were asking about what this was, so they're using this again because they're referring to the object itself that creates it. So now if we run it, then it's going to loop over these 2 rows and columns, so 21 by 21, and then for each it's going to do a translation, and then it's going to, it's going to do a push first of all, a translation, and rotate the cubes and pop it out again, and then it'll update the angle. So you'll see this running here. So you've got this mass of cubes that are kind of pulsing around. Thing. and see if I can break it by commenting out the push and the pop matrix. And then what should happen in that case is the rotations again will accumulate and it will go a bit haywire. So you can see that's not not really what you want to have happen. So
maybe slowed down. It could have a better fidelity or something.
Well, we can. We can slow it down. Let's see. Where's the rot?
Rot speed 2.0.
Oh, would you see that?
Under the ints. So
right.
7 here. Yep.
Okay, so let's change that to 0.2 maybe. See if we can make some art.
Sort of looks like it's materializing.
I don't know. It's kind of chaotic though, isn't it? It's just the good thing about processing is it's because it's interpreted, it's so easy to make changes like that. You don't have to recompile or anything. You just mess around and see what happens. Anyway, so that's a good lesson about make sure you use your push and pops, otherwise weird things can happen. So what I want to talk about now is the coordinate frames. So when you're doing 3D rendering, you have to set up a 3D coordinate system. And OpenGL and processing uses a right-handed coordinate system. So you use your right hand in X and Y, you curl around, and the Z comes out from the corner there as well. So the basic idea with the 3D viewing is that you have a virtual camera you're setting up. You've got some sort of object here, and then you're trying to, you have a view volume which is represented here, and then whatever's inside the view volume you want to make appear on a 2D plane. So inside processing you can set up all the camera parameters yourself. And there's this pipeline you follow through, and this is the OpenGL pipeline, but processing uses the same pipeline to get from the base coordinates in the object to what you see on the screen. So it's a little bit complicated, but basically what happens is you start off here with the, and I'll show a simple version of it later, you start off here with the raw coordinates. So if you've got your cube, you might have a 1, 0, 0 is in one corner and minus 1, 0, 0 is the other corner. And then you multiply those coordinates by a set of matrices until at the end you get a set of normalized coordinates which appears on the screen. So we'll go through those in a bit in each case. So the model view transformation is the first transformation. In this case what happens is that the objects in the 3D scene are transformed in the world coordinate space. So if you start with an origin, for example, here, and you want to move the cylinder around, then you do a world a model transformation, and then you have to transform again back into the eye coordinates. So these are the eye coordinates are what you see on the camera. So the two together becomes a model view transformation. So in the world coordinate frame, you move the object around, and then you have a camera set up, and you have to then know that you have to find the mapping from the object into the camera's coordinate frame. And this is how it's done in OpenGL, but the same thing is true in processing. So you start with a vertex here, and then you rotate through a rotation and translation. Well, I've got a spelling mistake there. A rotation and translation matrix, which moves the object. And then in front of that you apply a view matrix, and the whole thing together is called a model view matrix. So this view matrix is, so in this case, here's your object you're looking at, a wireframe sphere. Then you're applying a translation and rotation to the object, and then you're putting the camera in the scene, and the camera's set up here. So that transformation matrix multiplies through as well. So all three of them become the model view matrix. So I'll give you a couple of examples of that. So first of all, inside processing you can position the camera, and so in processing has a camera function. And the camera function, you have to pass it 3 parameters. You have to pass it where the camera is, so the eye position. You have to pass it the look at position, so where you're looking at, and also the vertical direction. So there's basically 9 values to set. And let me show you a demo of that. Actually, what was it called? Camera look at and camera move. Okay. So, so here's the camera look at here. So this is the camera function here, and so here the first is these three values are the eye position, and then the look at position is the origin, so it's 0, 0, 0. So what we've got is the camera is facing towards the origin, but the y value of the camera is mapped to the mouse y value. So as I move a mouse up and down, the camera's going to go up and down. But the camera's always going to look at the origin though, so as it moves up, it's going to rotate down to always look at the origin. And then you specify up vector, and then it's drawing a box with some lines popping out of the box. So this is what the overall effect is going to look like. So you can see as I move the camera up and down, mouse up and down in the y direction, the effect is I'm moving the camera up and down, and as I'm moving the camera up and down, I'm getting further away from the object, so that's why it looks like it's getting further away. And I guess just to keep you happy, let's change the, put the mouse X there and see what happens in this case. So now we're going to map the XY value to the, and we can, and now we'll get 2 degrees of motion. So now I can move around the object. It may look like from here that the object's moving, but actually the camera's moving, but it's hard to see that without any other reference in there. So that's one way you can set up a camera view in processing, is by using the camera function and then by specifying what you're looking at. It can be quite difficult to figure out what you're going to look at. So like if you're going to build a first-person shooter and you're using the keys to drive yourself around a screen, then it's hard to know where your look at vector should be, because you're going to be always changing the position in the... So there's other ways you can set cameras up too, and I'll show you that in a second. So then we also have this camera move demo. And in this case, it's doing the same thing, but what I'm doing now is I'm going to use the keyboard to move the camera around. So I change the look at position, and so I basically can drag with the mouse to change the look at position, and I can also use the keys on the keyboard as well. There it is. So you have to find your object first of all. Scroll down here. If I hit the... That's the right arrow, I think. I can't remember. Oh, there we go. So now when I move the mouse around, it's not very intuitive. But if I move in the Y direction, it's mapping it to the Z, or it's mapping it to the eye position. Yeah, and then if I move up in the X direction, it's doing the look at position there. So that's one way you could navigate with the mouse. This doesn't work as good as it could be though.
So you could map gestures from the Kinect or something to something.
Yeah, for sure. Yeah, definitely. Yeah, but I'll show you an easy way of doing it. So that's so what's happening in this case is that you're doing a view transformation, and what you want to do again is create a matrix. You can multiply them all together. So you have a transformation of the eye point, and then you have a transformation for rotation about the origin. So this is what the final matrix would look like if you first of all translate by an eye direction, and then you have to translate by rotation to rotate to look at the origin or look at your look at point. You get a final matrix like this. However, the cameras can have different properties as well. So in this case, we've just talked about moving the camera around, but you could imagine using a film metaphor, you could have a fisheye lens, or you could have a wide field of view camera or a narrow field of view camera, and processing lets you do that as well. So that's setting up the view volume. So we've just talked about moving the origin of the camera, but you can change the view volume to change the amount of object that's on the screen. So what the view volume is basically doing is taking an object point in the scene and mapping it back to the plane of projection. And then, so you're going from a 3D point to a 2D plane, and then drawing it so you can see the eye point there. So here's some of the math around that. You take, here's a given point here. If this is where your eye is here, then you can do some shape proportions to figure out what the height of this point should be compared to this point, using similar triangles to figure it out. And let me skip forward that a little bit. And so what you can do again is put that into a matrix, and when you multiply your points in 3D by this matrix, it compresses them down to 2D points that appear on a plane. And this is what's called a perspective projection. So let me just skip forward a little bit. I'll skip out the equations because you don't need to know those. But this is how you do it in processing. So you basically say you want to set up a perspective projection camera. And what you've got to do is specify the field of view in terms of degrees. Then you have to specify an aspect ratio. So is it a 16 by 9 or whatever the aspect ratio is going to be. And then you have to specify a near plane and a far plane. And those four things together create a pyramid kind of shaped volume. And then whatever's in that volume gets drawn on the screen. Yeah, let me show you a demo of that. And so this is all encompassed in this equation here, or this formula here. So let me show you a little demo of that running. So in this case, instead of calling a camera function and that looks at a location, what they're doing here is setting up a perspective camera. So here's a perspective camera here, and the field of view is being set by the mouse position, and then the aspect ratio is being set by the same aspect ratio as your screen, so the width over the height. And then if you push the mouse down, then it's going to change the aspect ratio by 2. So it's just going to set the perspective camera here, and it's going to draw 2 boxes. You'll see it here. So here are the 2 boxes, and as I said, you can see the field of view is set by the X position of the mouse. So as I move left and right, it's changing the field of view. It looks like it's zooming in and out, but it's not. It's just opening up or closing down the camera. So I'm not sure how many of you have done photography before. It's changing from a 28mm lens to a different lens. So it's the camera's not moving at all. It's just changing. And then if I hit the button there, it changes the aspect ratio to twice as much. So, and the Y value lets me rotate around the objects. So that's a perspective camera. And you can also set up an orthographic projection. So an orthographic projection is a flat projection, so it doesn't have any perspective. So normally when you're doing a painting or something, you always have perspective, and obviously objects further away appear much smaller. With orthographic, it's just a straight flat projection. So in this case, you have to specify a box, and everything inside the box gets drawn. And so you use this ortho command with left and right, bottom and top, and near and far, and those 6 values specify this box. So I can show you a demo of that running as well. So in this case, it's going to do 2 things. First of all, if I push the mouse down and hold down, it's going to show a perspective camera view. If I release the mouse, it's going to show an orthographic camera view. And you have to specify the left and right and the top and bottom. So in this case, they've just taken the width and they've figured out the left and right from the width. And they're going to draw a box here. So there's the orthographic view. But when I click the mouse down, this becomes a perspective view. You can see it's this one has the if it was had sight lines, you see the vanishing perspective going off in distance. Whereas this has no vanishing perspective, and it almost looks like an optical illusion. You can't see if it's inside or out. Yeah, popping in and out. Yeah. So those are different ways you can set up the cameras. And then, as I said, what they do is they create a view volume, and then everything that's inside the view volume gets drawn, everything outside gets So in this case here, everything inside that rectangle or that box gets drawn. Everything outside, you don't have to worry about drawing it because you can't see it on the screen. What generally happens though inside your rendering pipeline is that it'll normalize the coordinates. So even though you've got a rectangular shape like this, it'll make this to be -1 to 1 in all the directions. So you can apply a scale factor basically on each of the dimensions to normalize it all. And it becomes much easier for the renderer to know whether an object's inside or not because it can just look, it can just check them against -1 or 1. So you basically have a mapping where you take your projection view volume and you map it into a unit cube. And there's the equation that will do that. Cool, so we've gone kind of through this rendering pipeline here. We started off with talking about object coordinates and how to translate objects and how to position the camera, set the field of view, and then we finished up with normalized coordinates. And I've shown you that already. So I want to talk a little bit about lighting and color and then about texture, and then we'll take a small break. So if you've got an object in the scene, then you probably want to have it lit or have some color in the object. And the color of an object depends upon a number of different things. So it depends upon the light that's shining on the object, so where the light is, what color the light is, how far away it is, etc. It depends upon the geometry of the object, so if the object's casting shadows on itself or not. It depends upon the type of material, so is it a shiny object versus a not shiny. And it depends also on the illumination model and the shading model. So all these factors together play a role in lighting an object. So for example here, you may have a purple coloured object, but if you light it with yellow light, you may in fact get a blue reflection coming off the object. So when you look at it, the object may look blue, not purple, because of the interaction between the light and the colour. So a very simple illumination model will be the reflective colour is equal to the light colour times the material colour. Here's a more complicated, more realistic example. So in this case, you've got an object that's lit. I guess you'd say it's lit with a yellow kind of spotlight, and the object is purple. But you can see the final result across the range of the object here is very different, all the way from dark black through to blue, through to red and magenta, the original material. So it depends very much on where the light is and the interaction with the material.
Just for the bottom line especially,
yeah,
distinguishes between ambient and specular light.
Sure, yeah.
Is that indicative of how the information is stored on the computer? Like, is that an array or?
Oh, no, it depends. Well, they're all stored as effectively as vectors. So in this case, the ambient, diffuse, and specular light are all stored as vectors with 4 values. But what the outcome is depends upon the mathematical model that's used for them. So if you've got a simple illumination model like I showed before, you're just going to say the reflected light is equal to the light color times the material color. So here we've got the light is coming in as cyan, so it's got no red component, it's just got a green and a blue component. And if you multiply those together, then it's going to knock out your red component here, and all you're going to be left with is a blue component. So that's a very, very simple model, yeah. but actually there are a lot more complicated models than that. So and I'll show you a little more example. So all that's happening is it's taking those in your, well, I don't know with processing how exactly you can specify the light colors, but in OpenGL you specify the lights using a vector of 4 values, and then internally they've got a model that applies the lighting onto it. And then you specify the materials again by having 4 values. So here's some examples with processing several types of lights. So you can apply a point light, and a point light is a light which has a color and a position. So it starts off at a single point, and then it radiates out with a certain color. You can have a directional light. A directional light is the one that has a color and a direction. So you can imagine the light coming from the sun, for example, was so far away that for all intents and purposes, it's a light coming along a certain vector. So it's a directional light. The most interesting one is a spotlight, and a spotlight is where you apply a color, you define the position, and also a direction, but you also define an angle and a concentration. I'll talk about that in a minute, and that gives you your spots. let me show you in a demo example of that. So here's a lighting test, and in this case it's got several lights actually. So you've got a point light that's appearing here, you've got a directional light that's blue coming from the left, and you've got a yellow spotlight coming from the front. So if I run this, then what you have is a box, and as I move the box around, you can see the lighting affects how the faces of the box look. So I guess the blue light is coming from the left, so when you see the blue faces lit to the left. The yellow spotlight's coming from the front, and you've got an orange light coming from the right. You can see a bit of orange there. And I guess the yellow is interacting with the orange to produce red. Yeah. So the spotlight's a little bit interesting, because what happens in the spotlight is that it emits light along a ray vector, but then it emits it in a cone, and the cone depends upon the angle and the attenuation factor. So it has this cos to the it should be cos to the power of e theta, and so theta is the angle you're looking at, and the epsilon power here is the attenuation. So if you increase this a lot, then that's going to create a spotlight that's really very focused. If you decrease it, it's going to make it a very diffuse spotlight. So I'll show you an example of that working as well. So in this case, we have two spotlights and a directional light, and there's a sphere. And what you'll see is a lights appearing on the sphere. Yeah. Then the spotlight is moved according to the mouse Y direction. So if I click on here, then I can move the spotlight around, up and down. But I can also change the value. So if I make this very small, like down to 2, then it's going to make it very diffuse. So if I run that again now, then you see the spotlights covering the whole sphere. Or I can make it very big, like 10,000, and this is going to make it look almost like a pinprick of light, because when you've got a cos to the epsilon power, then the only case where it's going to get any significant is where it's going to be near to 0, because cos 0 is 1. So it's almost like a delta function, just a little spike. So if I run that, now you'll see a very small spotlight there. So that's how spotlights work. A couple more things and we'll take a break. So processing also supports the ability to load and manipulate images as well, and they have this p-image class. When you load an image into a p-image object, then you can get access to the individual pixel values of the image, and do some interesting things with that. So I'll show you a couple of example demos. First of all, I'll show you this is the picture I used. So here's a picture of some people wearing, I guess these are 3D glasses to look at a TV. So nothing too flashy with that picture. But there's an extrude demo. What the extrude demo does, it's like I've got to quit processing again. Let's restart it again. It's annoying, isn't it? Oops. Okay, good. That's good. Now I'll open the demo. Okay. Okay, so what the extrude demo does is it first of all loads the image up, the glasses image, and then it creates a pixel. It gets the value for each of the pixels, and it sets it to a color value, and then it finds the absolute brightness of the color and sets that to another value on here. So what's going to happen is it's going to take the color image and convert it to a black and white image, and then it's going to go through the whole image array and move the pixels in the Z direction according to their color. So you'll have this height map basically created. So let's have a look at that. So you can see there's this height map where dark pixels are lower than light pixels. Slowly rotating along. Other demo called Explode, and the Explode demo it's using the same picture. What it does in this case, though, is it moves the pixels around, and you'll see that. So it has this value cell size, and so it breaks up the whole image into a set of rectangles the same size as the cell size, and moves them around. And again, the key is that you can load the image in, and then you can get access to the pixels, and you can grab the color values of those pixels at different at each position of the image. So here it is here, and then when I move the mouse over, it explodes the image out. And so each of the pixels are quite small, but I could change the cell size. So let's change it to something like maybe 16. Now it's much more pixelated. So it could be a quite nice visual effect on something, I don't know. Yeah. But anyway, processing supports a whole lot of image reading functions that could be helpful. Let me see what else we're going to talk about. Okay. So I want to talk briefly about texture mapping. So so you don't just want to have objects that have flat coloured vertices, but you can also do texture mapping. And so in this case, you can map texture coordinates to the coordinates of an object. So the I must have my slides out of order. Let's have a look here. I had a whole bunch more. Yeah, there you all are. I made a mistake. So so obviously texture mapping is used to add interesting details to the surfaces, and you can also use texture mapping to simulate reflections. So this is an environmental texture map where you made it look like a reflection of the real world around it. And you can also simulate surface features like bumping or rough features by having a texture map that looks like it's kind of bumpy. So the basic idea is that you have an image, and you take the size of the image and you map it to coordinates between 0 and 1 along each dimension, and then you wrap those coordinates around the object you want to map to and apply the image, and then, hey presto, you produce a textured image. There's a couple of ways you can do it. One is using procedural mapping, where you have to manually create a bitmap that you apply to the object, but this is very rare. What normally happens is that you normally use images. So on the right hand side it's showing texture mapping using images. And so with processing, it's very simple to do. The basic texture mapping is very simple, and then they have some other code for doing more advanced texture mapping. But the basic idea is that you want to, with texture mapping, is you want to be able to find the color value at each point in the texture, and then define where it's going to map to on the physical object. So in processing, it's very simple. You just have to load an image into a texture object, and then you apply it using the text command. You can manipulate the texture coordinates, and away you go. So let me show you some demos of that. So here's the cube texture, and again, all I'm going to do is load in the glasses picture you saw before. I'm saying it's going to be normalized texture mode, which means it takes the the glasses image and maps it into a square 0 to 1 array. And then I'm drawing here, and then I've got a function for drawing the textured cube. So in that case, I just begin the shape, and inside the quad command, I place the texture command here, and that applies the texture. So you can do that very simply, and hey presto, there's a cube with a textured face on it. This is P3D, yeah. I'll show you in a minute with OpenGL, because it's can be different. And I've got another demo. Go texture. Oh, what's this one? Oh, okay. So this is texturing onto a single polygon. Yeah, you can see some interesting things going here. So when I move it like that, it looks like the polygon's bending, and that's because the texture map is warping. So it's actually not staying. It's not applying correctly onto the thing there. But I can comment out this. And if I just show a single triangle, then it would look fine. So now it looks fine without that, but yeah. And in this case, I'm going to texture onto more complicated objects, slightly more complicated object. So see here, it's texture mapping onto a cylinder. The cylinder has it's only half of a cylinder, and it's got a flat plane on the back there as well. So it's very, very easy to do texture mapping in processing. I want to take a small digression to talk a little bit about objects. And so I guess in processing you can represent objects as sets of vertices, but you can also represent them. I showed you last week the load object library that lets you load an OBJ file in, so you can represent whole files. One of the important things though is to think about when you've got an object made of different parts. So there's quite a lot of examples where you have a hierarchical model, like a robot or a composite structure or something. And in this case, you've got to think again about the transformations. So in the robot arm, you imagine this robot arm here, you want to be able to rotate the base around independent from the arms, and then maybe the lower arm rotates here and the upper arm rotates around this point. So you've got 3 different rotations going on. This rotation would be around the vertical direction, and these 2 rotations are probably going to be around the horizontal direction. So you'd have a whole set of matrices to do that. So you have to be very careful with your pushing and popping to make sure that you use that to isolate all the matrices. So in this case, this would be the OpenGL code for the robot, where you'd have this GL rotate that would then rotate the base, and then you translate till the bottom point of the arm. Then you'd rotate the lower arm, and then translate to the bottom point of the upper arm, and then you rotate the upper arm. Or you can have another example of a human where you've got to have a whole bunch of hierarchies. So in some cases when you're building objects and processing, you might build an object hierarchy. You'll have to think carefully about where you're going to apply your rotations. So there's a code for humans. Oh, and let's just go forward again. Actually, let's take a break for about 5 minutes or so. So maybe you can stretch your legs and you can stop recording for a minute. Almost out of time, so that's fine. So far I've talked about using the P3D library. I'll talk a bit about OpenGL graphics. And so what you can do very easily is you can swap the renderer from P3D to OpenGL. And so
Sorry, do you want to record?
oh, sorry. Right. Okay. So I've talked about using P3D graphics, but I'll talk about OpenGL now. And what you can do very easily is swap the renderer from OpenGL to or P3D to OpenGL. And all you got to do is change a couple of lines in the code. So let me show you that. I just got to find the right. A couple of demos I had before had OpenGL in them, and I think it's the push pop cubes. I think had. Let's see. Processing is still a problem. Okay. Okay. So if you remember, this is the push pop cubes running. Let's run it again. So it's all going there. So look at how that's running, and then what I can do is I can change to be the OpenGL renderer. And if you use the OpenGL renderer, then if you've got OpenGL supported hardware on your machine, then it uses that, and in many cases it will speed up the rendering and also produce more visually clean rendering as well. So all I need to do to change it is uncomment out this line here, comment this one, and make sure I have this included in as well. So you have to import the processing OpenGL library, but you just have to specify OpenGL in your size window instead of P3D. So if we run that one now, what you should see is the cubes going a lot faster. So they look like they're rendering probably, I don't know, 5 times as fast maybe. It's hard to see, but also there's not any aliasing on the edge of the cubes anymore. So they're much cleaner now as well. Yeah, so it's using OpenGL hardware in my Mac. I can show you also with the.
Can you increase the cube size just a little bit?
Yeah, your wish is my command. How would you do that? Let's see. Must be a
new cube.
12.
So maybe 18 by 18.
Oh, here.
Yeah. Just so they're like almost
let's
touching.
make it. Oh, okay, 18. Okay. I probably should increase this one a little too. Maybe to 8, 9 or something. Let's see what that looks like. Yeah. So that's again with using OpenGL, and now if I turn that off, and turn on the P3D, you'll notice that it should be running slower, and also they'll be more jagged. So it looks like it's, I don't know, 5 or 10 times slower, perhaps. Yeah, and you can see more jaggies on the edge. Anyway, so the most basic way you can use the OpenGL renderer is just by putting OpenGL in the size command there. I want to talk briefly about OpenGL, and I stole somebody else's slide so I can zip through quickly, just so you got a bit basic idea. So, okay, so OpenGL contains a mixture of both vector and raster graphics, and so the slide before was showing that with raster graphics you create images from pixels, whereas with vector graphics you create images from primitives like points, lines, and other shapes, and so if you scale them up, then they stay sharp, whereas with raster graphics when you scale them up, this might become pixelated. So with OpenGL you can do both, and you basically have this rendering pipeline where you start with the raw data, you then do some vector operations on the data, you do rasterization operations, and then some fragment operations, and finally it appears on the frame buffer and drawn onto the screen. And that's a very simple version. This is a more complicated version. It seems like a lot to learn, but actually it's pretty simple. Most of what we've done so far has been looking at geometry manipulation here in the processing to date. So you take some vertices, you move them around, or put them into an object and move the object around, and then the rasterization is where it gets drawn to a 2D part of memory, and then it creates the fragments and draws it onto the screen. Then you've got two paths basically. This path specifies what happens to all the pixels, all the vertices, and this path here specifies what happens to all the images that you might use, like for textures as well. We won't talk about it here, but the most recent version of OpenGL supports shader programming. And what shader programming does is it's small programs you can apply to each vertex in a object, and or to each pixel in a image. So it's a very different way of programming. So instead of defining a whole object and moving a whole object around, you define a set of vertices, and then you have a small code fragments that apply to each vertex or to each pixel in the array. And processing also supports that as well, but it's more complicated to write those types of programs. So OpenGL is a state machine. What that means is that you, as a programmer, you set it into different states. So you tell it whether or not you're going to go into a matrix mode or not, or whether you're going to go into what type of camera mode you go into. And the basic OpenGL API, you have function calls like this. So all the methods, all the functions are prefixed with a small GL, and then all of the types are prefixed with large GL, and all the constants that are uppercase. And you have a bunch of user-defined types. So drawing is pretty simple. Just like with processing, you have to have a begin and end, and then inside that you say, draw. In this case, it's drawing one vertex at a point 10 by 10. So typically, you have a GL begin, GL end block, and you draw everything inside the block, and then whatever you draw inside the block appears. So in this case, this won't be drawn because it's outside the begin and end block. And you can specify different types of vertices, which is different from processing. So you can have integers and floats, doubles and booleans, things like that. There's also a set of primitives, much the same as processing. So here's the primitives that OpenGL has. So you've got lines and strips and loops and triangles and polygons and quads. And then you have a set of points as well. And in most cases, you'll create vertices and then use GL points to join them all together. So you can join points into lines and loops or triangle fans or quads. And you can create polygons by creating closed loops of points. So in processing, you can use OpenGL just by changing the size option and by importing the library. But also you can create your own OpenGL renderer and then directly access OpenGL commands. But you run a risk by doing that because not all OpenGL commands are supported by processing. So processing uses something called JOGL, which is effectively a Java wrapper around OpenGL, and not everything is supported by that. So let me show you an example of a program that uses raw OpenGL. And I can't find it. Oh, how embarrassing. Vertex demo, spotlight demo, sphere move. Oh, here we go, OpenGL points demo. Okay. So this is using another library called the Anticode library, which is basically a wrapper on top of OpenGL that lets you load models and things like that. And in this case, what's happening is they've in the draw function, you have to first of all you have to create an OpenGL renderer. So here's your OpenGL renderer, and then once you created the renderer, you have to call a begin GL command and an end GL command, and then inside that you can draw your drawing. And what they're doing here is creating a points list, and they're rendering a set of points. So, and this library supports what's called a GL model, so it loads all the points into the GL model and then renders from that. So if I run this, it's just going to create a point cloud. There's the point cloud right there appearing. Can I see it? Oh yeah, yeah. So in most cases you won't need to use the OpenGL code, but sometimes you might want to explore with, if you've got an OpenGL program you want to get running in processing, you could easily get it running as well. I think that's most of what I want to talk about there. Great. So for the last little bit, I want to talk a little bit about Arduino, but I want to do it in the context of, well, I've got a couple of other presentations I got from other people I wanted to show you. Two in particular. One was talking about the LilyPad, and the LilyPad is an Arduino board that we don't have. So let's show that for starters. There we go. Great. Okay. So this is a PowerPoint presentation I grabbed from this other woman. Her name's Rain Ashford. And what she does is she builds clothing that has electronics in it. So we'll just skip through it quickly and you'll get a sense of what she's talking about. And the main piece of hardware she uses is this lily pad here. And the lily pad is basically an Arduino, but it's designed on a flexible circuit board, and it's easy to connect different objects through these connectors on the side here. And especially good for doing embroidered circuitry and wearable electronics, because you can get conductive thread and loop them through the links here. Okay, so let's skip forward a little bit. So this is what she does. She creates wearable works of art using lots of different, primarily Arduino and other sensors as well. And so here's the LilyPad microcontroller. And so it's a circular shape here, and you can use it with conductive thread, and then connect to the conductive thread you can connect a bunch of sensors and actuators and other devices as well. So the good thing about it is that you can easily sew it, so it's quite easy to sew into devices, and it's open source, and it's got a lot of I/O devices. The slightly bad thing about it is that it's a fixed size board, and it's not as cheap as she would like, but it's not expected. So here's some of the devices, the artwork she's put together with it. So this is a dress that glows in the dark. She had, this was a mood generator, and so depending on what mood she was in, the green cat or the red cat would glow. And this was a monitor for her galvanic skin sensing, and a little crown she built. Yeah. So let's skip through that. So I really want to talk about the sensors, and so what she's been looking at is how you can combine different sensors and actuators with with LilyPad. And I guess in the labs you've played with this a little bit, haven't you? Yeah. So she's got an infrared sensor here, for example, and in the cat example, she had it set up so that the cats would glow only when somebody was standing in front of her. So she'd use the infrared sensor to figure out if somebody was there, and then the cats would light up. And I guess the idea was if she was in a bad mood, you shouldn't talk to her or something. So, you know. So here's some other types of sensors that she's been interested in using. So you can look at things like RFID sensors or heart rate sensors, gas or chemical. Basically anything you can get an electric signal from, you can plug into the Arduino and use as a sensor. So here's a bunch of sensors and actuators that she's been looking at different contexts. So in a sports context, for example, you might want to look at your heart rate or your GPS, and the actuators you might be able to have as LEDs or LCD displays. In a military context, you might have motors or servers, so you might have a mechanical device that does something, and you might have to get a lot more biosensor information off somebody. In fashion, you might use electroluminescence, or you might use RFID or Wi-Fi as sensors as well. So here's some more examples of the types of electronic devices. This is actually a tattoo, and somebody's tattooed, I don't know how that worked, some thread into their skin or something. So this may be an RFID tattooed into their skin, I'm not sure. And this guy has solar panels all over his camouflage. I don't know how that would work, because it seems like you'd ruin the camouflage, but anyway. So for example, here's a sports device, and this combines a heart sensor, blood oxygen, respiratory and temperature, and then you have a little LCD that plugs in what your heart rate is and everything there. Yeah, this is epidermal electronics. So it sticks to the skin, I guess, like a tattoo, and it can monitor heart rate and muscle activity. And then here's some lightweight solar panels that are flexible, and they also absorb light on both sides, which is quite useful. This is a intelligent yarn, so it has a strain gauge inside it, and it can also measure light as well. And here's some electroluminescent and thermochromic ink, so she has a lightning pattern that lights up on her her skirt. I've got no idea what this is. A conductive pom-pom. There we go. Mm-hmm. So that gives you some ideas of what you can do with this type of hardware. So that was a nice little snippet. I want to show you another more complicated example as well, which is a nice design example called Wanderlust. And I'll actually go to their website. So Wanderlust is an interesting project that was done with Arduino and followed the same design process we've done already. So the project goal was to design a mobile service. It was a project funded by Motorola, and it was design a mobile service tailored for creative people so they could use their identities to allow them to explore new spaces and to meet people who had similar interests. So Motorola was basically interested in understanding how phones or other devices could facilitate human relationships and connect people and also their physical environment. And so the person put together a really nice thesis, and I'll put that online as well. Let me just go back to their website. Oh, here it is here. Okay. So this is their thesis, but it's a short thesis, but I'll put it online and you can read through it. But they have a really great blog which talks about the design of okay. I'll get into it before. I think it's just blog. It talks about the design of their there we go. Okay, so this is the design process they went through. I'll show you a few slides now. So first of all, there's a brainstorming process, and we've talked about that before. So they did a whole set of post-it notes and ideas about what type of user interfaces or experiences some sort of mobile device could provide. And from that, they decided they wanted to focus on communication and focus on different types of communication. So the idea was you could have a person with a device could shout, and everybody within a certain range of the person would get a message from them, or they could glance, and so this is broadcasting out to connect to people, but being indiscriminate, so everybody who's within a radius of you can get a message on their device. And then you have a glance, and so what a glance does is where you look and try and find the interests of people around you, and they change the representation of the people depending upon how similar they are to your interests and to your social network. So this means here, the small little figure says a third degree on your social network, so it's 3 degrees removed from you, so it's a friend of a friend of a friend, so you don't know them that well. The darker figures have the darker the figure it is, the more common their interests are. So this person here, who's large and dark, is probably an immediate friend who has a lot of common interests to you. So that was a way of you querying out to see what people are like. Then you could also listen. So this is where you just listen to basically all what other people are doing around you, and you could drift. And the drift mode showed you what potential areas of interest there were, or objects of interest there were around you as well. So where you had nothing in mind you wanted to do, but it just showed you potential buildings or locations that might be interesting to you. So those were the kind of their idea for how a user interface might work. Then to make it real, they did, first of all, they made a wire diagram. So this is what their wire diagram looked like. So it's very rough screenshots. So you log in and put a password, and then you from here you can go into shout mode where you shout a question to your community, or drift mode, so what's going on, or listen, I'm available for some fun. So you set into different modes on your device, and then based upon that, different interactions happen. So, here's I'm available for some fun, and then you set your availability, like what time you're available, and then you can receive a message from somebody who wants to have fun with you. And the other ones use different methods as well. So one of the more interesting things was the user interface, and I'll show you their evolution of the interface, which is kind of interesting. So here's their concept creation. And very slow loading. This is the design process they used. I see there's some pictures there, but I guess not. And these are the user interface designs they put up there. So they blogged everything while they were doing it, and so they had a really good set of. Rough designs. So first of all, I have a graphical user interface like this, so you could log in through the web and put all your details in the web. But the more interesting thing was that they, on the device, had an interface like this, but then they decided they wanted to change a little bit, and they actually implemented they implemented a ViewMaster metaphor. So the idea was you picked up the ViewMaster and looked into it, and then you would see in the ViewMaster this type of screen, and then you could interact with it using the slider bar. So they the way they did that is they had a physical ViewMaster disk, and the disk had an RFID tag in it, and you'd pick the disk depending upon what network you wanted to connect with. So if you wanted to connect with your Facebook network, you'd get the Facebook disk and you put it into the ViewMaster, and then on the screen you would see your list of Facebook friends and you can navigate through them. So here's the Facebook appearing here, and then here's some of your friends appearing, and this is the well, this one says I want to drink beer, so you're now going in the you're in the mode where you're trying to get people to take you out somewhere. But I thought it was very interesting because it combined a physical, tangible interface with this screen object. And then what they did to build the physical interface is they used that, you can see down here, they developed several physical prototypes. So, okay. So first of all, they had a prototype running on a UMPC. So they got a small PC touchscreen, and they had it running with the interface in the front end. So you could touch it, and you could now communicate with people and glance or drift or whatever. You can see it's still a ViewMaster metaphor, but it doesn't look at all like a ViewMaster, but they just want to get it working. So this is done up in Flash, and you just see it working. Sorry?
Rotating the other way, like
yeah, could have.
the right direction.
Yeah.
I guess I've got to somehow represent like navigation, like backwards and forwards.
Sure, yeah. So there's your interface working there. Then what they did is they here's all the coding they did for it. So that was the first prototype.
Is this on like a iPhone or something? Or are they actually using the ViewMaster?
Well, you see. So the second prototype, they got the ViewMaster, and they took it apart, and inside the ViewMaster they put a RFID reader. So here's the different disks for your social networks. So each of those has an RFID tag in it. So you got your LinkedIn. I guess is it MySpace? Or one of the yeah, and Flickr and or maybe Facebook. I don't know. And then inside that they put a the Arduino to control the RFID reader, and they also connected a mobile phone in there, and they used the mobile phone screen to show the information on. So here's what it all looks like. So and you had the mobile phone just showing in one eyepiece, but the mobile phone was connected to the Arduino, and then so the Arduino is telling what images to show. And I don't know if there's a video of that working. I don't think there is. Yeah. So I was really impressed with that. I think I've got a couple more slides here. Oh yeah, pretty much what I just showed you. Yeah, so there's the view, and there's the final ViewMaster interface. So I was really impressed with that because they went through the whole interaction design process, and then they had a very interesting tangible object at the end, and they were able to use the Arduino in an interesting way to get it to work. And it seemed quite natural. If you wanted to connect to your Facebook friends, you'd grab the Facebook disk and put it in, and then you got your Facebook friends looking up through there and everything. I don't know if that's you wouldn't really go out in the real world with the ViewMaster and start looking around, but you could imagine how you could enhance that by having GPS and having other locations going there and everything. So the last thing I wanted to show you, we're almost out of time, is I just wanted to, I found another really good set of slides around Arduino, and I wanted to flick through a couple of them so you could see. So this is, and I'll put these on the website as well, this is the a class that was taught by a computer science lecturer from the Interaction Design Centre, and he was talking about why Arduino is so valuable, and so he basically said it's valuable because it combines these three things. You've got the reasonably good hardware, you've got a pretty nice development environment, and then most importantly, you've got a very, very active community. So when you bring those three things together, you get a huge amount of support and tool building you can do. So let me skip forward a little bit. Here, different examples. That was not so interesting. It was quite interesting, his classification of Arduino in the middle here. Okay, so here's some resources, and I guess we'll probably end up buying some of these books. The Making Things Talk, I've seen that in the bookshop. That's a really great book about how to add physical interactivity to toys. But he provides us a very interesting diagram here showing where different types of prototyping tools sit. So you've got this category here of how easy is it to use, and the other category up here is how expensive it is. So you've got things like Lego Mindstorms, which are very, very easy to use. You've got visual programming, you can plug it in, but they're also pretty expensive. You've got to pay like $300 or $500 to get a decent Mindstorms kit. And you got across the other side here, you can do your own low-level hardware programming. So that's very inexpensive, but it's also very, very complicated. So Arduino kind of sits in this nice space here. So he says with the Mindstorms, you've got expensive but friendly. And the Arduino sits down here, which is seems like it's sufficient for most needs. I'm not very familiar with wiring. Do you know wiring at all, Mike?
Yeah, wiring is the project that Arduino is actually based on. It was created by researchers at MHIT.
Oh, okay.
The problem with wiring was their board was proprietary and you don't get it from those guys.
Oh, okay.
Never really got much of a problem.
So when Arduino open source the hardware, then yeah. So you've got these three kind of extremes. You've got the Mindstorms, which is expensive but friendly. You've got the Arduino here, and then you've got chips and PCBs at the end. And this little graph showing the costs. So here's the Lego Mindstorm with gripper. Here's the Arduino, and here's an AT Mega 168 chip. And the prices, this one costs about €250. This one costs about €25, and the chip costs around €4. So obviously this is the most inexpensive, but the amount of time it would take to use this in a project would probably easily make up for the money you're saving there. You do, yeah, and you know, yeah. So, and in fact, this chip is the one that's in there anyway. I won't go through programming in Arduino because you know all that now, but he had a couple of interesting things at the end here of other different interesting projects. I'll just show you. So there's some other interesting ways to use Arduino. One is through using pure data. So I don't know how many know pure data, but it's a visual programming tool that lets you wire different objects, different ports. So here's this block here represents your Arduino, and then you can wire out and you connect each of the pins on the Arduino board to other different devices just by drawing lines between them. So it's very, very easy. There's also Flash, and a simple Flash example is processing, which you know now. And here's some example projects. The lily pad, which we just talked about. Here's the wanderlust. So, which is sure. And yes, and that was about it. There's one last thing I want to show you, which I thought was really cool, was this guy's, maybe I can't find it, let me just have a look. This guy did a project with Arduino. I had the website, but then I had to reboot my Safari and I lost it, so that was not great. Let me see, is it this one? No, not this one. Is it? No, not that one. Not that one. Not that one. Maybe this one. Oh, well, this is another interesting tool I thought was Quartz Composer. which is another visual design tool which could be useful as well. So it's very easy to plug things together. But interesting projects. No. Let's Google for it, and if we can't find it, then we'll break. Let's see here. It was basically a really cool project where the guy had written here it is. So it's a Twitter. When he wrote a project, so whenever he got a Twitter feed, then it would blow bubbles from this little bubble machine. So you could. He was at this conference, and where's the video? There's another video on his page, which is better. Hang on. Main site is bubblino.com. Okay. Yeah, so it's a little robot with that blows bubbles when you go. I thought that was a pretty cool application of Arduino. So whenever you send a message to @Bubblino, it'll start blowing bubbles. So he talked about in his the slides I can't find. He talked about how he was able to build that with an Arduino board. It was pretty simple. He had he had the Arduino controlling this, and the Arduino was connected via Wi-Fi to another machine that was monitoring Twitter feeds. And then whenever it got a message, it would send a message to the Arduino that would then rotate the bubble thing and actuate it and cause it to blow bubbles, which is kind of a nice. I guess that's one of the powerful things about Arduino is it makes it very, very easy to connect the physical with digital environments. Wow, and he's selling them for £235. That's great. Very expensive. Anyway, that's all for now. So we'll break, and I said on Tuesday I'll have a class about open frameworks, and then I'll also give you an assignment to do over the holidays and the first week back. So.